Welcome back to Tech 293 on Thursday, February 25th. In this second video, we're going to finish up talking about ferrous metals. All right, we left off right here giving some examples of different types of steel. And we're going to talk a little bit more about the percent carbon that you would have in a steel, because there are good reasons to have a low amount of carbon or a medium or a high amount of carbon. Generally speaking, the less amount of carbon you have in a steel, that's going to make it cheaper, it's going to make it softer, and it's going to be more ductile, and it's going to be easier to machine. And so this is a good application for sheet metal, and you might use that for structural shapes as well. Generally, the more carbon you have in the material, the stronger and harder it's going to be, but it's also going to be less ductile. All right, so if you go all the way to the other side to high carbon steel, it's going to be harder and stronger. It's not going to be as ductile. And so if you want to make tools out of steel, which is really common, if you want to make tools out of steel, then the tool steel needs to be able to cut and shape the other steel. And so the way that you make something sharp and able to cut something is by making it very hard and then sharpening it. So when we talk about tool steel in a little bit, when you want to make a tool out of steel, you want to put a lot of carbon in it. You want it to be a pretty high carbon steel. It's going to be strong and hard. If it's hard, that means you can sharpen it and it will hold an edge. However, the downside to high carbon steel, it's not going to be as ductile, and therefore it's not going to be as tough. All right, I have an example for that. Here's like a dumb me type story from a couple of years ago. So a couple of years ago, I was changing a tire on my car. And so I got out the jack on my car. And it's one of those scissors jacks that has the scissors that kind of start out like that. And then you crank it and it opens up like that and it jacks up the car like that. That's the kind of jacks that most cars come with. Anyway, I had the scissors jack. I had it under my car. I was ready to jack up my car, but I couldn't find the tool that you use to rotate. That you rotate the tool and then it rotates the little screw on the scissors jack to open up the scissors jack and jack up the car. Anyway, I couldn't find that thing that you rotate to cause the jack to get taller. So I went into my garage and I just grabbed the first thing that I found, which was a file. I found a file that was, probably like that long or something like that. And it had ridges on it like a normal file would have. And I just grabbed that because it was a piece of metal and it was about the right length for me to put it into the scissors jack and rotate and make the scissors jack get taller so it would jack up my car. Well, anyway, I put that file into the scissors jack and I start to crank on it, and I probably got a little ways. I got the car jacked up a little bit, but then as I had to put a little bit more force into it and I had to put some torque on that file to crank the jack, it just snapped because it was pretty brittle, because it was a file and it was made out of high carbon steel. And high carbon steel is not very ductile and it's not very tough. Right? So because it's not very tough, it can't absorb much energy before it just fails. It just fails abruptly. So anyway, I don't remember what happened. It's not, the car didn't fall off the jack or anything, but I just wanted to give an example of how if you want to use a part that needs to have some toughness to it, don't grab something that has a high carbon steel, a high carbon content, because it's not going to be very tough and it's just going to be brittle and it's just going to snap when you don't want it to snap. So if you want something to be tough, then you want to use something that has a medium amount of carbon. And generally our definition for medium carbon is somewhere between 0.3 to 0.6% carbon. Less than 0.3, you're talking about low carbon steel. More than 0.6, up to, it says here 1.6%, but that's a lot. That's a real lot of carbon. You're almost up to cast iron at that point. So anyway, more than 0.6% carbon, you're in high carbon steel territory. But between here, 0.3 to 0.6% carbon, we'll call that medium carbon content. This is oftentimes the sweet spot for a lot of different mechanical components that you want to be strong and kind of ductile, and more importantly than anything else, tough, if you want it to be tough. So this is a great application for gears and drive shafts and lots of different components that you want to be able to absorb a lot of energy before they just give way and fail. All right. But on the other hand, you don't want gears and drive shafts to be real ductile either. I mean, some ductility is fine, but you don't want them to be real ductile. So a medium carbon content is a pretty good medium, happy medium for a lot of different types of applications. All right, so the amount of carbon you have in your steel has a big impact on the mechanical properties of the steel, how ductile it is, how strong it is, how hard it is, how tough it is, things like that. If you were to do a stress strain curve on different classes of steel, low carbon, medium carbon, high carbon, this is what you'd look like. This is what you'd see in the stress strain curve. The low carbon steel is much more ductile, so it's stretched out in the horizontal dimension, in the strain dimension, but it's not that strong, so it never gets very tall in the stress dimension. In contrast, the high carbon steel, it's not very ductile, so it fails at a pretty low strain, a pretty low amount of strain, but it is the strongest, and so it's the highest in the vertical dimension, which is the stress. It can handle more stress, which means it has a higher strength than the other materials. And the medium carbon steel is the toughest because it has the largest area under the stress strain curve. So it has medium strength and it has medium ductility, but what it does maximize is the toughness of the material. So in general, as you add carbon content to a steel, you're going to make it all of these things. You're going to make it more expensive. It's going to be less ductile. It's going to be harder. It's going to be stronger, so it'll have a higher tensile strength. It will have a lower melting point. We haven't talked about that yet, but it's true. If you have more carbon, then it's easier to do heat treatment on it. We haven't talked about that yet either. We're going to talk a lot more about heat treatment in the last third of the class. And to be able to do heat treatment, you need to have carbon in that steel. It can't be pure iron. If you have pure iron, you can't heat treat it. You got to have carbon in there to accomplish the heat treatment. Also, as you have more and more carbon, it becomes more and more difficult to machine in general, including to weld. A few specialty steels that I want to talk about just briefly for each one of these. The first one is tool steel, and I already talked briefly about this. If you want a tool steel, you want to make a tool out of steel, then that steel needs to be able to cut and shape other metals, including steel, right? Like low carbon and even medium carbon steels. So the way to do that is to use a high carbon steel for tools. That will make it strong and hard. And if it's hard, then you can sharpen it and it will hold an edge. And so that's what we use to make files and saw blades and things like that. You use a high carbon steel, oftentimes with a bunch of additives added into it. The carbon, obviously, you want a high carbon. Also things like chromium and molybdenum and tungsten, these things down here, vanadium also. So you add a bunch of alloy metals to it, and that tends to make it stronger. Also, another important thing is heat treatment. So usually what we'll do is we'll take a high carbon steel that has these alloying elements in it to begin with, and then we will also do a heat treatment to it to make it even harder. And if it's even harder, then it will do a good job of holding an edge and maintaining a cutting edge to shape and cut other metals and materials. Here are some examples of different kinds of tool steel. High-speed steel, those are actually the cheapest drill bits. You can get other drill bits that have other more expensive alloying elements added to them. But high-speed steel, that's one kind of tool steel, one of the cheaper kinds. A2 is another kind of tool steel. Air hardened is another kind. And this is what a lot of the additives are that you use to mix in to make the tool steel. All right, stainless steel. Let's talk a little bit about stainless steel here. What you do to make stainless steel is you add a whole bunch more chromium. So we're talking like at least 10 or so percent and up to 20% chromium. You add that to a low carbon steel, and what happens then is when the steel with chromium in it, when it reacts with the oxygen in the air or water around it, with normal steel you get iron oxide, right? You get iron oxide, which is rust. And the problem with rust is that rust tends to flake away. It peels away, which exposes new iron, which exposes that new iron to oxidation, which forms a new layer of iron oxide, rust, and then that peels away. And you keep on peeling these layers back, and eventually you're left with nothing. So when you leave your basic iron or steel out in the rain, out in the elements for a while, you know that you're going to get a rusty piece of iron. And eventually you leave it out there long enough, it's just going to kind of disintegrate. It's just going to fall apart because all of that iron has been converted into iron oxide, and the iron oxide peels away. It's not part of the lattice structure. It's no longer part of that lattice structure. What's important about chromium is that chromium and also the nickel that's embedded in it, what they do is they form a substance called chromium oxide. So the chromium interacts with the oxygen in the environment. It forms chromium oxide, and the important thing about chromium oxide is that it does not peel away. It doesn't disintegrate or fall away from the lattice structure. The chromium oxide remains bonded to the lattice structure of the steel. All right, so if it doesn't peel away, then it doesn't expose the new surface to further oxidation. And so it's actually like the oxidation layer around the outside of the material actually protects the rest of the material inside that material. All right, so it's just the outer layer of the material that actually oxidizes and forms chromium oxide, but that's called a passivation layer, otherwise known as a passive oxidation layer, and it actually protects the material underneath it so that it does not oxidize. And it's all about the chromium oxide remaining a part of the lattice structure of the steel. All right. Okay, the last thing that we'll talk about is cast iron. There are a couple different kinds of cast iron that we're going to talk about. Cast iron has a much higher carbon content. It's usually somewhere around 2% or even more, maybe 4% even for cast iron. And when you have that much carbon in the material, you can't roll it and you can't forge it, because if you do rolling or if you forge it, it's going to just break because it's so brittle. And so what you have to do with cast iron with such a high carbon content, you have to cast it. So you have to create these forms or molds, and then you get the cast iron into a molten state. So it's really, really hot, it's a liquid, and then you pour it into the mold, and then it's kind of like injection molding for plastic. Once the cast iron has cooled, then you break away the mold, and now you're left with the cast iron part. So here's an example of casting. You pour the molten metal into this hole right here, and then you form your casting right here. All right, I've said some of this that has a high carbon content. So the casting process, it tends to work well for kind of bulky parts. It does not work well for parts that have small little delicate pieces, because it just doesn't fill in those small delicate pieces in the casting very well usually. Another thing to consider is that cast iron tends to work well in compression when you're squishing it, but it's usually not very good in tension because it's brittle. Right? So in general, we can say that cast iron tends to be a pretty good material to choose if you've got kind of a large or a bulky part that doesn't have that many details. And maybe it benefits from large mass, you know, just a physically big part. Those are the parts that tend to be made of cast iron. I'll give you an example. When I worked on wind farms for GE, the bed plates for the wind turbines, in other words, the frame, not the tower section, that was rolled, but the bed plates of the nacelle, which is the top section of the wind turbine. That bed plate was oftentimes cast. It was usually a cast iron material. But in general, lots of these different material, these different applications down here are good for cast iron applications. Anything where you've got like a base or a pedestal, bed plate. Oh, hubs too? Yeah, that's right. Wind turbine hubs, those were cast also. All right, so we're going to talk about 4 different kinds of cast iron. And the differences between these 4 types of cast iron have to do with a couple of things. Number 1, it's the carbon content. So you can adjust the carbon content of the cast iron. Number 2, it's the grain structure of the carbon. So what form does the carbon take inside the material? That makes a big difference in how the cast iron behaves. Thirdly, you can add alloying materials, other materials that you add in that change the behavior of the cast iron. And lastly, heat treatment. Heat treatment is yet another thing that we can use to adjust the mechanical properties of the cast iron. All right, so the first and most basic type of cast iron is called gray cast iron. It's the most common. It's got very high carbon content. It also includes a little bit of silicon, 1% silicon. And all of this makes it very brittle, but it's also relatively soft, and it's pretty easy to machine. The reason that it's brittle is because naturally, as the material cools down and solidifies, the carbon, and there's a lot of it, all of that carbon solidifies into a shape that looks like flakes. Like they literally look like, you know, think of like corn flakes or Raisin Bran, something like that. So the carbon literally solidifies into these flakes, and the problem is that those flakes act as stress concentrators. And to give you an example of a stress concentrator, here I made a quick example of a stress concentrator. Here is a sheet of paper, and I just cut a hole right in the middle of it. So let's say I was going to do a tensile test of this, and I'm going to pull it apart. Where would you guess that this material is likely to break? So it might not even have to be paper. Imagine this was plastic or metal or something like that. So you might guess that it's going to break right along this line right here because I've got a stress concentrator right there. What this hole does is it concentrates the stress right around the vicinity of this hole. You can even look at it like, well, the cross-sectional area right here is less than the cross-sectional area in other parts of the specimen. So when I apply a force to it and cause a stress, I'm actually going to cause a higher stress in this area right around this hole, because it has a lower cross-sectional area right here than is going to be in the rest of the part. So up here and here, far from the hole, I have a larger cross-sectional area, and so I have a lower stress. So if I were to pull this apart, then I would expect that it would fail somewhere around this vicinity near the hole in the part. And that's true not just for a flimsy paper part, that's true of plastic and metals and woods and all kinds of materials. So this is why gray cast iron tends to be very brittle, because that carbon that solidifies, it tends to solidify in flake form. And those flakes have lots of sharp edges that have a tendency to form cracks that serves as a great starting point for cracks to form in the material, and it contributes to higher stress in the material around those flakes and in the vicinity of those cracks. All right, the next step is you can have material called white cast iron. White cast iron has a lower carbon content than gray cast iron, and it is subjected to a heat treatment process that makes it harder and more brittle and also makes it more difficult to machine, but also stronger than gray cast iron. One important thing in here, I didn't write this in here, but when you do this heat treatment, what happens is the carbon gets converted from the carbon in flake form in gray cast iron. It gets converted into a material called cementite. And cementite is something that we'll talk about when we talk about heat treatment, but cementite is very hard and very strong and also brittle. And so white cast iron is characterized by carbon in the form of cementite. The last two are malleable cast iron and ductile cast iron. And malleable cast iron actually starts as white cast iron, the last one that we just talked about, but it has a further heat treatment called annealing. We'll talk more about annealing later on in the class. But what annealing does in general, it makes things more ductile. In the case of cast iron, specifically what it does, it takes the carbon and it transforms the carbon into spheres, which we call nodules. And the nodules tend not to form those cracks in the material as much as the other types of cast iron. So the nodules are not nearly as effective of stress concentrators. They don't tend to form the cracks in the material as well as the carbon flakes in the gray cast iron. All right, so malleable cast iron tends to be a lot more ductile, especially than the gray cast iron, but it's even more ductile than the white cast iron. The last kind is called ductile cast iron, or just DI for ductile iron. It has quite a bit of carbon in it, 4% carbon, but the key thing here, it has an alloying element, specifically magnesium. And what magnesium does is in the cooling process, as the cast iron is cooling from a molten material, it encourages most of the carbon to form into nodules instead of flakes. And so it has similar physical properties to malleable cast iron. It's a lot more ductile and not nearly as brittle as gray or white cast iron. It also tends to be pretty tough, and it's strong and easy to machine. So DI is really commonly used for lots of mechanical components like engines and crankshafts and pipes. And here's a microscope image of ductile iron showing the carbon nodules or spheres versus the flakes of carbon in the gray cast iron. So these flakes of carbon tend to do a really good job of acting as stress concentrators, and they form cracks at the tips of the carbon flakes, and it causes the material to be much more brittle, whereas this shape of carbon tends to cause the material to be quite a bit more ductile. All right, there are a few more slides in the appendix, but I'm not going to go through those. You have all these slides, so you can go through those. It just shows a bunch more pictures in the appendix, so it shows a bunch more pictures of different types of cast iron, and it just goes through all the pictures of the things that I just talked about. So that's going to conclude our presentation on ferrous metals, and I'm going to stop the video here. In the next video, we're going to talk about the procedure for Lab 5 and how we're going to do Lab 5, which is tensile testing of metals and woods. So I will see you in the next video.